afternoon. For problem solving, we have prop beam of length L and loaded shown. We're going to solve the reactions R1, R2, and M2 using double integration method. Take point 1 as the origin of our xy plane and consider section 3 at the distance x from the origin. EIY double prime is equal to the moment of 3, wherein moment 3 is the sum of all moments at the left of 3. Hence, we will have EIY double prime is equal to R1x minus WO times x minus a multiplied to the moment arm, which is half of x minus a. Simplifying, we'll have EIY double prime is equal to R1x minus WO over 2 times x minus a squared. The first integration will have EIY prime is equal to R1x raised to 2 over 2 minus WO over 6 multiplied to x minus a raised to 3 plus constant value C1. Remember the power formula, and this is the slope equation, and we can call this equation 1. In the second integration, EIY is equal to R1 over 6 times x cubed minus WO over 24 multiplied to x minus a raised to 4 plus C1 times x plus another constant C2. We can call this equation 2. Applying boundary conditions at point 1 at origin, we'll have to set conditions at x and y. X equals 0 and y equals 0, then substituting the values, therefore we'll have C2 equals 0. Point 2 is a fixed support, hence x is equal to L, and since at this point the deflection at slope is 0, y is equal to 0. Substituting at equation 2, we will have 0 equals to R1 over 6 times L cubed minus WO over 24 multiplied to L minus a raised to 4 plus C1 times L. Transpose C1 will have WO over 24 times L multiplied to L minus a raised to 4 minus R1 over 6 times L squared. There we got C1. Again, using y prime equals 0 from equation 1, we'll have 0 equals R1 over 2 times L squared minus WO over 6 multiplied to L minus a raised to 3 plus C1. Solve for C1, then we'll have that equation. That's another value for C1. To solve for R1, we're going to equate these two values, C1. We'll have the following equation, then arranging it, we'll get this kind of equation. Solving for R1, we will have 3 multiplied to the right side of the equation and cross multiplied L squared, and there we'll have the reaction R1. Observing, we know that L minus a is equal to b. So we will have this kind of equation for R1. And lastly, factor out the WOB cube over 8L cube, therefore we'll have the value for R1. Summation of forces in y direction gives us positive R1 and R2 and negative WOB. Transposing R1 to the right side and substituting its equation will result to the following equation. Lastly, simplifying it will give us the reaction R2. Lastly, for M2, we will solve using the moment at the left side of 2. We will have M2 equals to R1 times L minus WOB multiplied to B over 2. Substituting equation R1, we will have the following equation. Then factoring out negative WOB squared over 8L squared, we will have the value of M2. Therefore, the answers are the following equivalent equations. Thank you.
Hi, my name is Matthew Bernardus and I will be discussing a sample problem with the method of superposition. Determine the midspan value of EI deflection for the beam loaded as shown in the figure. Use the method of superposition. So as you can see here, we have a single beam divided into three with a length of 2 feet, 4 feet, and 3 feet with a total length of 9 feet, and two concentrated loads with a force of 100 pounds and 80 pounds. So first you would need to figure out on the formula that we can use for these types of concentrated loads. So as you can see, we have two concentrated loads at the beam, therefore we can use the formula of deflection would be equivalent to the summation of PB over 48 EI multiplied to 3L squared minus 4B squared. This can only be used when the condition of A is greater than B is applied. So how can we know if this formula can be applied? So for this example, if we want to solve for 80 pounds, our A will be here at this part at the left side of 80 pounds. Why? Because 2 plus 4 is equal to 6. Therefore, 6 feet is greater than 3 feet. So this will be our A and this will be our B. So that's how we'll find the deflection for the 80-pound force. However, with our 100-pound force, we cannot apply that since at its left side we only have 2 feet and at its right it has 4 feet plus 3 feet, which is 7 feet. Therefore, we can use this as our A and this as our B. Therefore, 7 is greater than 2. So, the logic or the formula is EI deflection midspan is equivalent to EI deflection midspan due to the 100-pound force plus EI deflection midspan due to 80-pound force. So we can use the formula of EI deflection midspan is equivalent to the summation of PB over 48 multiplied to 3L squared minus 4B squared. So first we will be solving for the EI deflection midspan at 100 pounds. So as I said earlier, we're going to use this as our A and this side as our B. So we have 7 feet as our A and B as 2 feet. Our load of 100 pounds and the total length of 9 feet. So all we have to do is input this in our formula. So 100 multiplied by 2 divided by 48 and then multiplied to 3 times 9 squared minus 4 times 2 squared. This will give us a total value of 945.833 pound cubic feet. Next step would be to solve for the 80-pound for deflection at the 80-pound force. So we're going to use this as our A and this as our B. So we have a load of 80 pounds, B of 3 feet, and total length of course 9 feet. And again, we can input this in our formula. Therefore, our formula will consist of 80 multiplied by 3 all over 48 multiplied to 3 times 9 squared minus 4 multiplied by 3 squared. And this will give us an EI deflection at 80-pound value of 1035 pound cubic feet. And of course, the final step is the summation of EI delta of both concentrated loads. So that will be equivalent to 1035 pound cubic feet plus 945.833 pound cubic feet. That will give us a summation or a total of 1980.83 pound cubic feet. So that's it for my problem. Thank you.
Hello, my name is Elimatthew David, and I will be discussing another sample problem in beam deflection by using method of superposition. For the problem, calculate for the midspan deflection of the beam loaded in the figure with the length of 4 meters by using method of superposition. The Young's modulus of the given metal is 10 gigapascal and the moment of inertia is 20 times 10 raised to 6 millimeter raised to 4. And here in our figure, we can see two different loads. First is the 2 kilonewtons, which is a concentrated load where it is located 1 meter away from R sub 1. And for the second one is the 1 kilonewton per meter, which is an example of uniformity distributed load over the entire span of the beam. For the given, I listed here the value of the length, Young's modulus, and moment of inertia. To understand more the given beam figure, it is the combination of two cases from deflection for common loading by method of superposition. First case is the concentrated load at any point on simple beam, and second case is the uniformity distributed load over the entire span of simple beam. For the first case, we will be using the formula for deflection at the center where it is not maximum, which is delta is equal to concentrated load times B over 48 times de Young's modulus and moment of inertia times the quantity of 3L squared or 3 length squared minus 4B squared, wherein the value of A is greater than B, where delta is equal to the deflection of the beam, P is equal to the concentrated load, B is equal to the distance of the concentrated load from the support, and length, Young's modulus, and moment of inertia is given in the problem. For the second case, we will be using the formula for the deflection at the center, which is the delta is equal to 5 times W sub 0 times length raised to the fourth, all over 384 times the Young's modulus and moment of inertia, where the deflection is the delta, W sub 0 is the uniform distributed load over the entire span of the beam. For the equation of deflection in midspan, it is the sum of the deflection due to the concentrated load at given distance and the deflection due to uniform loading. To simplify, we substitute the two formula that we discussed for the two cases. I listed here the given and then substitute to simplify the equation. In my solution, I multiplied both sides of the equation with the Young's modulus and moment of inertia to reduce the equation, and I came up with the deflection in midspan multiplied by de Young's modulus and moment of inertia is equal to 31 over 6, and the outcome of the unit is kilonewton meter cube. To get the value of deflection in midspan, transpose de Young's modulus and moment of inertia to the other side. Then we get 31 over 6 kilonewtons meter cube over 10 gigapascal, which I use Newton over meter square, times 20 raised to the 6 millimeters raised to the fourth. And then we simplify the millimeter to the quantity of 1 times 10 raised to negative 3, then raise it to the fourth power to make the unit of meter raised to the fourth. And then simplify the two exponents, negative 3 and 4, which we will be multiplying since negative 3 is raised to the fourth power. To understand more what happens to the unit, let's refer to the box solution. The first term here is Newton times cubic meter all over Newton per square meter times meter raised to the fourth. Then to simplify, cancel both the newtons and reciprocate the square meter to cancel out the unit in the denominator. Then meter raised to the fifth power divided by meter raised to the fourth power is equal to meter, which is our final unit for the final answer. For the next slide, I've included another solution in simplifying the moment of inertia to, to get the deflection of midspan. Since 1 millimeter raised to the fourth power is equal to 1 times 10 raised to negative 12 meter raised to the fourth, we can substitute that here for the value of our moment of inertia. In this equation, we reciprocated the 1 times 10 raised to the negative 12, making it positive 12 and negative exponent negative 4 for the meter. To understand the solution, we will refer to the box solution. Here we have Newton times cubic meter all over Newton per square meter times meter raised to the fourth. Then cancel both newtons, leaving cubic meter times meter raised to -4 all over the quantity of 1 over square meter. Then multiplication of same terms with different exponents, leaving meter as the final unit for the deflection. Here we have the deflection of midspan, which is equal to the 25.83 millimeters. The moment of inertia, or second moment of area, is a property of the shape that is used to predict deflection, bending, and stress in beams, although it is not related to the length of the beam or the material of the beam. The relationship between the moment of inertia and beam deflection is inversely proportional, so larger moment of inertia means less beam deflection. For my reference solution, I listed here my source. Thank you.
So, good afternoon to everybody. Good afternoon, Sir Disolo. My name is Cedric Erne, and I'm here to discuss another sample problems about the superposition method in beam deflection. So, let me read first the problem. The beam shown in figure P689 has a rectangular cross-section 4 inches wide and by 8 inches deep. Compute the value of P that will limit the midspan deflection to 0.5 inch. Use the modulus of elasticity 1.5 times 10 raised to 6 psi. So, first we need to identify the given. So, we are given a rectangular cross section of 4 inches wide by 8 inches deep. Next, we are given the midspan deflection to 0.5 inches. And lastly, we are given the modulus of elasticity of 1.5 times 10 raised to the 6 pounds per square inch. And also, we are given in the graph below uniform loading, which is 2,000 pounds per feet. And we're given each section of 2 feet, 10 feet, and 2 feet. So, first we're gonna do in this problem is to identify the case. So, in the case of this problem, we have three cases involved. Number one is the case number 8, case number 11, and case number 12. So after identifying the cases, we will be using this formula. For case number 8, there, we will be using this formula. For case number 11, we'll be using this formula. And lastly, for case number 12, this formula. So, yeah, let's go. So, we have to compute for the magnitude of end moments and the moment of inertia. So for the magnitude of end moments, we will denote this as M. M is equals to 2,000 pounds times 2 multiplied by 1 plus 2p, which is equals to M is equals to 4,000 plus 2p. For the moment of inertia, we will be using I is equals to BD cube all over 12 is equals to 4 times 8 cube all over 12. And the moment of inertia is equals to 512 all over 3 inches raised to 4. So we can now compute for the for the value of P since we got the magnitude of end moments and the moment of inertia. So we will be using this formula in solving P. So uh, so here we just have to substitute all the values that we are given. 0.5, which is the given of midspan deflection, is equals to 5 multiplied by 2000 times 10 raised to 4 times 12 raised to 4. But that is the actual length of the beam. So 384 times 1.5 times 10 raised to the 6th power, the moment of inertia which is given, 5, 512 all over 3, which is we solve the moment of inertia minus 2 times magnitude of the moment, which is 4000 plus 2p, 10 squared times 12 cube all over 16 times 1.5 times 10 raised to the 6th power, 512 all over 3. So after that, we'll be computing this formula and we will get this. And after simplifying this one, we will be arriving to this equation. And then our end goal is to find 2p. We have to find p. So we just have to transfer negative 1 negative 27 multiplied by 4000 plus 2p to the left hand side, and while the 160,000 is will be going to the right hand side. So 562,500 minus 160,000 is equal to 402,500. Then 27 4,000 plus 2p. So we just have to divide them by both side by 27. So, and after we going to divide 27 to both sides, we will transfer 4,000 to the other sides. So, after doing so, we will be arriving to this equation. And the final step in to answer the problem is divide them by 2. So our final answer is P is equals to 5,453.7 pounds. And that's all. Thank you everybody for listening.